Hello everyone, this is the first of a series of videos dedicated to kinetics. In these videos we will study what reaction rates are and will describe some of the factors affecting reaction rates. We will be also studying types of reactions and will describe them and find out how we can assign them as a zero first and second order reaction. We will study something called the collision model that tries to explain how reactions take place at a molecular level. And we will also be studying activation energy and specifically the use of catalyst to increase the speed of reaction. We will look at several examples of the use of different types of catalysts. As usual, this video is divided in several sections to make it easier to follow. Kinetics, chemical kinetics, deals with the speed of a chemical reaction, what we call the reaction rate, and its reaction mechanism. Kinetics tries to describe the change in concentration of the different chemicals as a function of time. And you can do that in a qualitative form. For example, in this graph, we have here how a reagent reacts to form a product, and slowly over a period of time there are fewer and fewer molecules of reagent and the molecules of product are increasing. Or you can also do it in a quantitative form by calculating specific reaction rates at particular points in time. And here the different lines A, B, C, D and E describe reaction rates at different points in time in this reaction, and how the concentration of this particular chemical, in this case ozone, decreases as a function of time, and specifically at what rate it decreases. Chemical kinetics can tell us how chemicals react to form products, and this aspect of kinetics studies the mechanism of a reaction. It also will tell us how long will it take for the reaction to reach completion. And changes in concentration as a factor of time also feature strongly in kinetics, and also looks at the effects of catalysts and enzymes in increasing the reaction rate, the speed of a reaction. We can define a reaction rate as the speed at which reagents are converted into products in a chemical reaction. So if we look at our reaction A, reagent A to produce product B, the reaction rate would be the change in concentration divided by the change in time. And you can define that reaction rate with respect to the reagent or with respect to the product. If you define it with respect to the product, what you're looking at is how much product is formed in a particular period of time. If you're looking at it with respect to the reagent, what you're looking at is how much reagent has disappeared, has reacted, again as a function of time. And if you notice, when you define a reaction rate as in the function of a reagent, you put a minus sign in front. And that is because the amount of reagent is going to decrease over time. So the difference between the concentration of reagent at T2, a future point in time, with respect to how much it's at T1, a previous point in time, is going to be a negative number. And we do want our reaction rates be positive numbers, which is what the minus tries to avoid. And if you look at the graph here, if you represent time with respect to an alleged number of molecules in our inventor reaction A to give product B, you see that initially you start with only reagent and no product, but over time, let's say here at 30 seconds, the amount of the reagent will have diminished, and clearly the amount of product has increased because the reaction is taking place. What factors affect a reaction rate? Well, there are three key factors that will affect the speed of your reaction. One is the concentration of the reagent. So as the concentration of reagents increases, there is more likelihood that those molecules of the reagent will react to form the product. That there is more likely that they will collide with each other to form the product. There's also temperature. The higher the temperature, more kinetic energy the molecules of your reagent will have, and they will move faster and will collide more often and with greater energy. So again, more likely they will form the product. And finally, there is the use of catalysts. There are compounds that can help speed up a reaction, but changing its mechanism. Let's look at an example of a reaction rate using this reaction, the hydrolysis of butyl chloride. You have a butyl chloride that reacts with water to produce butanol and hydrochloric acid. And this is a table of the concentration of butyl chloride at particular times from 0 to 10,000 seconds. So if we look at our reaction with butyl chloride, we can calculate different average rates for each interval in which the reaction has been measured. So for example, if we calculate the average rate of reaction over the first 50 seconds, if you plug in the numbers, you will get that is 1.9 10 to the minus 4 moles per liter per second. And you can calculate an average rate for each 50 seconds interval, well, for each period interval that has been measured. And as you can see, the values slowly decrease. And that's quite common. It is quite common that the average rate decreases over time, and we can dwell more into why that is in future slides. So it is unlikely that your reaction will have one average rate for the whole reaction, because it is likely that your reaction rate will have different reaction rates depending on what point in the reaction you are measuring that reaction rate with respect to. If we plot the concentration of butyl chloride as a function of time, what we have is a curve. And we can use the slope of a line tangent to that curve at any point in time to calculate the instantaneous reaction rate at that time. And that's more interesting because, as I mentioned before, the reaction rate is not fixed throughout the whole reaction, but changes on time. So it's more useful, rather than calculating an average reaction rate for the whole reaction, it's more useful to calculate an instantaneous reaction rates at particular times that you are more interested. So the slope of that line tangent to that particular point will tell you the instantaneous rate at that particular point in time. And as I mentioned before, rates change, or can quite happily change, as the reaction proceeds, and typically they will slow down.